Testing. Okay, so before we get started on chapter 5, before we get started on chapter 5, any questions concerning the assignment chapter 4? If not, well, let's move on to chapter 5 then. So chapter 5, we'll be dealing with a couple of topics. I would say mainly centering around the properties of water, right? And water is kind of unique among different substances because water is absolutely necessary for life here on Earth. And just an information here given about water and the percentage in different situations. So it says here, water covers 70% of the Earth's surface. And as far as the human body is concerned, it composes 60% of the human body, 50% of our blood, and 77% of our brain. And as I said before, water is very essential, especially to us human beings. And as you can see here, some information about the extent to which we can do without water. It says loss of 2% of your body's water leads to thirst, 5% you start getting headaches and fatigue. If you lose 10 to 50%, then you start experiencing muscle spasms and delusion. And then if your loss of water is greater than 50%, then it would lead to death. And they're making the point in the last line that fresh water is a very limited resource. Okay, so this is an exercise that you can probably do on your own, keeping a water log. I'm going to skip that and talk about the composition of water. So we know that water is made up of two elements, hydrogen and oxygen, right? And the formula of water basically gives you an indication as to the number of hydrogen and oxygen molecules present per molecule, all right? So that's a composition. But in terms of the structure, what you'll find is that the actual structure and shape of the molecule looks something like this, all right? Well, this is a space-filling model, but in terms of this representation here, you'll see that the oxygen is simultaneously bonded to the two hydrogen atoms. And you'll notice also that the molecule is bent in shape, all right? In fact, the angle here has been measured between the two hydrogens, and it turns out to be equal to 104.5 degrees Celsius, right? So what you're going to see is how this shape of the molecule and other features relates or correlates to the different properties displayed by water. As stated at the very top, it says water is a liquid under standard temperature and pressure conditions of 25 degrees Celsius and 1 atmosphere. And when you compare water to other compounds of similar molecular masses, you'll see that water is a liquid while the other substances are gases. Another thing about water is that its boiling point is unusually high, 100 degrees Celsius. And when you compare that to a similar molecule like H2S, H2S is pretty much a gas under normal room temperature conditions. So that shows you that water is very unique in this regard. Another thing that is unique about water is that when water freezes, the volume increases, all right? It expands. And if you live or if you have lived in regions of the United States where it's cold during the wintertime, you all know that there's a danger of pipes bursting when the temperature falls, right? Falls to the point where the water in the pipe is freezing, all right? And that's because it expands. And this is related to a phenomenon known as hydrogen bonding that we're going to talk about shortly. Now, that makes water also unique because most other liquids will contract when they freeze, right? But water is unique. In fact, as far as I know, water is the only substance which expands when freezing, all right? Okay, so before we get to the actual structure of water, I need to talk to you about this concept of electronegativity, right? It's basically a measure of the attraction of atoms for electrons that are shared with another atom, right? So the greater the electronegativity, the greater will be the attraction of the atom for the shared electrons. And some values that work well, a scale has been developed by a guy by the name of Linus Pauling, and it's based on some thermodynamic calculations. And he came up with the scale where the most electronegative element will have a value of 4.0, which is, in this case, fluorine, and then all other elements were determined based on that. So what you're looking at here is a small sample of the different elements and their associated electronegativity values. I have a more comprehensive, I have a more comprehensive table. Let me just show you what it looks like. We go to files, and then let me go to tables, and then let me go to table chemistry. I don't think I have to download. Let me just scroll down here. I think it's the last page right here. So this is a more comprehensive table with the different electronegativity values of different elements. So this is what you'll use if you're required to use it when it comes to questions involving electronegativity. Okay, so let me go back to the PowerPoint here. And so let's talk about what we call polar covalent bonds as opposed to non-polar covalent bonds, right? So another term for polar covalent bonds, we say that they're polar bonds, all right? Now, in the case of a polar covalent bonds, this typically happens between two different atoms that are sharing electrons with each other. But because one is more electronegative than the other, the electrons are not equally shared. They're shared but not equally, right? The electrons that are shared will be attracted to the more electronegative atom, right? So we have what is known as a bond dipole, which is basically a measurement of the polarity of the bond as a result of unequal sharing of electrons. And we represent the direction of the dipole by using an arrow, as you can see here. For example, in the case of hydrogen bonded to oxygen, the arrow is pointing from the less electronegative atom to the more electronegative atom. So as you can see here, hydrogen has a value of 2.1, oxygen has a value of 3.5. The difference between them is 1.4, all right? And as you can see here, the arrow is pointing towards the oxygen. So that's basically how we represent what we call a bond dipole. Now, in the case of a non-polar covalent bond, that is typically formed between two atoms of the same element, like chlorine, oxygen, and nitrogen, which are all diatomics. We tend to see that because, of course, both atoms are identical, so they will have the same electronegativity value. So therefore, there's no unequal sharing. The electrons shared between them would be shared evenly, and therefore the difference in the dipole or the difference in the electronegativity values would be zero. So therefore, we say that such bonds are non-polar covalent bonds, all right? Okay, so that's the difference between non-polar covalent bonds and polar covalent bonds. And what you see is that whether or not a bond is polar or non-polar will have some influence on certain properties that substances will display. Now, we'll be talking about water, of course. And as we said before, this is the shape of the water molecule, right? Now, in this particular case, we can, before I even say what I was about to say. So we just talked about the fact that bonds can be polar or non-polar. Well, it turns out that a molecule can be polar or non-polar, and it depends on not only the type of bonds that exist, whether or not those bonds are polar or non-polar, but also the shape of the molecule. So here's an example. In the case of the water molecule, we know that it's bent or V-shaped, as you can see here, and the direction of this dipole is in that direction between this hydrogen and this oxygen, and this is the dipole in the case of this bond. And as you can see, they do not cancel out each other exactly. So because they do not cancel out each other, we say that the water molecule is polar. Now, that is different from beryllium chloride, as you can see here. In this particular case, the molecule is linear, right? There's a straight line from the chlorine through the beryllium to the other chlorine over here. So therefore, this dipole will be acting in that direction, and this dipole will be exactly linearly opposite, acting in that direction, and therefore they will cancel out. So as a result, the beryllium chloride molecule is said to be nonpolar because the dipoles cancel out. But in the case of the water molecule, the dipoles do not cancel out each other. And therefore, we say that this molecule is polar, all right? So what you'll find is that the polarity will have some influence on the properties displayed by the different substances. Now, another important feature of water is the fact that it can form what we call hydrogen bonds with each other between water molecules, all right? So a hydrogen bond, as stated here, is basically a force of attraction that exists between the hydrogen atom that is bonded directly to an atom of nitrogen, oxygen, or fluorine, and an atom of nitrogen, oxygen, or fluorine. So in other words, there are a couple of things that you need for hydrogen bonding to take place. You need a hydrogen atom, which is bonded to either these three elements, nitrogen, oxygen, or fluorine, and then you have a nitrogen, oxygen, or fluorine of another molecule that will form what we call the hydrogen bond with the hydrogen, which was previously bonded to nitrogen, oxygen, or fluorine within its molecule. So we can use the water molecule as an example of how we can establish the hydrogen bond. Here we have the oxygen bonded to a hydrogen, and then we have another water molecule which also has a hydrogen bonded to oxygen. What will happen is that there will be a strong attractive force between this oxygen and this hydrogen. This oxygen from this molecule and this hydrogen from another molecule. So you have a strong attraction here, you have a similar attraction here, you have a similar attraction here, similar attraction here, right? So these are what we call hydrogen bonds, and these should not be confused with the covalent bonds that exist within the molecule, right? So in this case, the hydrogen bond, we say that these bonds are intermolecular because they exist between molecules, but the covalent bonds are intramolecular because they exist within a molecule, all right? And the hydrogen bonds play a very important role in terms of the properties displayed by water, right? In fact, what you're going to see here is that the hydrogen bonds, even though they are not as strong as covalent bonds, but they're strong enough to impart certain physical properties of water. For example, the high boiling point of water that we talked about earlier is actually due to hydrogen bonds. They're relatively strong, and therefore, if you want to boil water, in order to convert it to a vapor, you have to heat it to a relatively high temperature so as to break those hydrogen bonds, and therefore the molecules can escape as individual gas molecules, all right? That's very important, of course, in terms of water being able to carry out certain functions on Earth. For example, if there was no such thing as hydrogen bonds, then water would not exist as a liquid under normal temperatures, right? And therefore, there will be no seas, no rivers, and we won't be able to consume water, or the water won't be able to carry out the functions in our bodies and so on. So hydrogen bonds are very important in terms of determining the properties displayed by water. So two key things that are mentioned here, and that is that chemical changes are governed by the strengths of the intermolecular covalent bonds and polar bonds, and the physical changes are governed by the strengths of the hydrogen bonds or London dispersion forces. In this case, we're focusing on hydrogen bonds. All right. So another consequence of hydrogen bonding is that it results in the solid state in a very open structure, which is the reason why ice expands, or why when you freeze water to form ice, there's a corresponding increase in the volume, it expands. And that's because as it adopts the three-dimensional structure that you see here, it becomes more open, and therefore the solid phase is dense. The solid phase of ice is less dense than that of water. As I said before, that is highly unusual for substances. Most substances, the solid phase is more dense than the liquid, all right? And as stated here, aquatic plants and fish can live in freshwater lake during cold winter because the lake doesn't freeze from bottom up. And that's because ice is less dense than liquid water, so therefore the ice forms on the surface while water will exist in the liquid state below. And therefore you can still have aquatic life below the ice as a result of that, all right? If the opposite is true, or if the opposite was true, then basically aquatic life would be negatively affected if it freezes from bottom up. But that's not the case, as I said before, because solid ice is less dense than liquid water, all right? Another consequence of hydrogen bonding is the fact that it has, water that is, has a high value for these particular quantities. The specific heat is higher than most other substances, again, because of hydrogen bonding. The heat of fusion and heat of vaporization are also relatively high, again, because of hydrogen bonding. And again, the reason for these values being relatively high is because of the relative high energy needed to break these hydrogen bonds as you go from the solid state to the liquid state. Okay, some general information here about water. I think I mentioned this earlier. 3% of water is found on Earth is fresh water. 68% of all fresh water is in the glaciers, ice caps, and snowfields. 30% of fresh water is found underground and must be pumped to the surface. And then you have 0.3% of fresh water that is present in lakes, rivers, and wetlands, right? And as stated here, if all the water on our planet would fit into a 2-liter bottle, only 60 mils would be fresh water. So that gives you an idea as to how scarce fresh water is, right? And it said only 4 drops would represent the water in lakes and rivers. And this is just basically giving you a kind of representation diagram showing you the relative quantities of the different types of water sources. Okay, let me just skip all this here and get to, you can read this up on your own. I want to get to this, a discussion of solutions, especially when it comes to water, all right? And solutions where water is a solvent. So I think we mentioned this term before, solution, same thing as a homogeneous mixture, which is basically a uniform combination of 2 or more substances. And in the case of water-based solutions, what you'll find is that the water would be the major component, and we call that the solvent. And the other components in the solution we call the solute. So the majority component of a mixture is called the solvent, and the minority components would be the solutes, which are dissolved in a solvent, right? So if water is a solvent, then we call that solution an aqueous solution. So we can determine or measure what we call the percentage, or I should say the concentration of solution, which is basically a ratio of the amount of solute present for a given amount of either solvent or solution. And there are different ways of measuring or calculating the concentration. We have what is known as percent, which is the same thing as parts per 100, right? In other words, what part of 100 grams of a solution would be the solute? So for example, if you have 20 grams of sodium chloride in 100 grams of solution, then we say that the solution is 20% sodium chloride. But you have some other ways of expressing concentrations. You have also what is known as parts per million and parts per billion. And these are typically used when it comes to very small concentration values. So for example, 97 parts per million calcium is the same thing as 97 grams of calcium in 1 million grams of the solution. And we can actually convert that using these 2 conversion factors to get the same value in terms of milligrams per liter of solution. We multiply first by this, which is basically the density. You write this here. So this here is basically, oh gosh. Okay, so this here is basically the density of the solution. And then once we get the mass of the solution, because how should I put this down? The grams of solution here and here will cancel out. So basically we're going to be left with the liter of solution here. And then what will happen is that this gram of calcium will cancel out this gram of calcium. So you'll be left with milligrams of calcium above here. This 1,000 and this 1,000 will cancel out this million right here. So therefore you end up with the same numerical value, but this time is expressed in milligrams per liter of solution. And down here is a similar calculation. The only difference is that we're talking about parts per billion, which is the mass in grams per billion grams of the solution. We do a similar calculation. The only difference is that at this point, we're talking about the microgram of mercury in 1 gram of mercury. That's a million. So basically, by the time you do your cancellation where this cancels with this, and this cancels with this, and you're gonna have 1 times 10 to the 9, well, actually 1,000 divided by 1 times 10 to the 9, that will cancel out with this because that will be equal to a million. So this, and this will cancel out. And again, you're going to end up with the same numerical value as in the case of parts per billion. But this time, the units would be micrograms of mercury per liter of solution. All right, so that's, those are a couple of ways that you can express the concentration of a solution. I would say that the most common way in chemistry of expressing the concentration is by this particular way of determining it. It's called the molarity. And the molarity by definition, as you can see here, is the moles of the solute divided by the volume of the solution. All right. And the abbreviation in terms of the units could be moles per liter, which is the same thing as uppercase M. So whenever you see uppercase M, you should understand it's the same thing as moles per liter. And in chemistry, we use square brackets to indicate concentration of whatever is within the square brackets in units of M. So for example, this here represents concentration of sodium chloride is equal to 1.0 M, which also means that there's 1 mole of sodium chloride for every liter of the solution. All right, so that's yet another way of expressing the molarity of a solution. Okay, so here's a question. It says, how many grams of sodium chloride are in a liter of 2.0 M sodium chloride? So basically, what we need to do first is start off with the 2.0 moles per liter, right? And then actually what should happen here is, so basically what we do first is multiply the molarity by 1 liter. That's what the question is asking for. And then that would give you the moles because this will cancel out with this. And then it says in the next step, you're going to multiply the mole value by the molar mass. Of course, you get the molar mass by adding up all the molar masses of sodium and chlorine in that compound according to that formula. And then you do your number crunching and you end up with your answer here in this case, which is 106.9 grams of sodium chloride. So that's a relatively simple example where you're given a molarity, you're given a volume, and you're asked to find the mass of the solute that is present. Okay, now how do we actually make up solutions of specific molarity? Well, in the case of molarity measurements, we use this piece of glassware that you see here on the screen. It's called a volumetric flask, right? They come in different sizes. I think the smallest one I've seen is a 10 ml flask, and then the largest one I've seen is a 2 liter flask, right? The thing about these flasks is that they are made very accurately. They're made specific to measure a particular volume, right? Because what they have is a line that is etched on the stem right here, right? That line represents a specific volume if you add liquid to it and the liquid gets up to that mark, right? So if you add 1,000, if you add liquid, in this case, it's 1,000 mils. If you add a liquid to it until the mark is reached by the liquid here, by the surface of the liquid here, then you know that you have 1,000 mils of solution in that flask, right? And this is the type of flask that we use to make solutions of specific molarity. So let's say you want to make 1 molar solution of sodium chloride, right? The incorrect way of doing it, let me explain the incorrect way first. The incorrect way of doing it is after you find the mass of sodium chloride, which is equal to 1 mole, what you should not do is add water up to the mark and then add the sodium chloride after, right? That is incorrect. Because when you add the sodium chloride after, you cannot guarantee that the volume, the final volume is going to be the same, right? So the correct way of doing this is that you add your solid to the flask first, then you add water until the water gets up to about here, and then you stopper it, then you shake it to make sure that everything dissolves, and then after everything dissolves, then you continue to add water until the water gets up to the mark here, and then you stopper it another time and you shake it just to make sure that the solution is homogeneous, and then that's it. And that's typically how we make solutions of specific molarity. So a couple of key things here you need to remember. You need to determine the mass, right? Because there's no direct way of measuring the moles, right? So you have to use the molar mass to convert the moles to mass in grams. Then you put it in the flask, and then you add water till it's about half full, and then you make sure it mixes, and then you add more water until you get to the mark, and then you mix it again, and that's basically how you make up the solution. All right? Okay, any questions so far? Any questions? Any questions? All right, so let's look at some questions here. It says express the concentration of 16 parts per billion mercury 2 plus in units of molarity. So how am I going to do this? Because I'm going to need some space. Okay, let me get out of this here. And let me insert a new slide. Yuck. Okay, so just to remind myself of what the question is saying. Okay, so you're starting off with 16 parts per billion, and you're trying to find the equivalent molarity, which would be, erase this here. Which would be expressed in moles per liter. So I'm going to put moles per liter. All right, so the first thing I'm going to write down is 16 parts per billion is the same thing as 16 grams over 1 times 10 to the 9 grams of solution. So this is for the mercury 2 plus, and this would be for the solution, all right? The next step is I would convert the grams of solution to volume. Now the assumption is that 1,000 grams of solution would be equal to 1 liter of solution, all right? So basically I'm gonna put 1,000 grams up here of solution and divide that by 1 liter of solution, all right? Then I would focus on converting the grams of mercury to moles. So here I'm going to put 1 mole of mercury 2 plus, and the molar mass of mercury is
something.
where is it? Oh, 200.6 grams. So I'm going to put 200.6 grams of mercury 2 plus down here. So what's going to happen in terms of units canceling out? You're going to have grams of mercury 2 plus canceling out here and here. You're going to have grams of solution canceling out here and here. So the only thing that would be left is moles of mercury 2 plus divided by liters of solution, which is basically molarity. So let me get my calculator. Okay, so 16 times 1,000 divided by 1 billion divided by 200.6. Okay, so according to my calculation, this works out to be equal to 7, let's call it 8.0 times 10 to the minus 8 moles per liter. So that's basically how that is done. All right? Any questions about this? Any questions?
So you times it by 1,000 and then divide it by.
Yeah, well, the way I enter it in my calculator, I times the 16 times 1,000, then I divide by 1 times 10 to the 9, and then I divide by 200.6. All right, any other questions about this? Okay, the next question, let me scroll back up. It says, for 1.5 m and 0.15 m sodium chloride, how many moles of solute are present in 500 mils of each? Okay, I'm just going to do for one of them, and then you can probably work out for the other one. So I'm going to start with the 1.5 m. So for the 1.5 m of solution, of sodium chloride solution, the volume is 500 mils of the solution. I'm going to multiply that by molarity, which is 1.5 moles of sodium chloride for every 1 liter of, well, let me put 1,000 mils, which is the same thing as 1 liter, so that I can cancel out the milliliter unit. In fact, you know what? Let me do the longer way so that you can see stepwise how this is done. So what I'm going to do is convert this to liters. So in other words, I'm going to have 1 liter of solution above. What's wrong with me? Okay, so 1 liter of solution above and 1,000 mils of the same solution below. And then the next conversion factor is where I multiply by the molarity, which is 1.5 moles of NaCl for every 1 liter of solution. And then I multiply this by the molar mass, which is 58.5 grams of sodium chloride for every 1 mole of sodium chloride. And then I do the number crunching, which is 500 divided by 1,000 times 1.5 times 58.5. So according to my calculation, this works out to be equal to 43.9 actually grams of sodium chloride. And that's how that is done. And then you're going to do a similar calculation for 0.15 m sodium chloride. So the only difference is that instead of 1.5 here, you're going to have 0.15 here, which means that the answer here becomes 4.39 grams of sodium chloride. All right, so that's basically how that is done. Any questions? Okay, let me see what the B part is saying. Okay, so it says a student is asked to prepare a 1.0 liter of a 2.0 m copper 2 sulfate solution. The student placed 40.0 grams of copper 2 sulfate solution crystals in a volumetric flask and filled it with water to the 1,000 ml mark. And the question is the resulting solution 2.0 m? Well, in order for us to answer that, we need to determine the molar mass of copper two sulfate. So, can somebody tell me, let me do it up here. What's the molar mass of, copper?
63.55.
Okay, so 63.55.
Yep.
And what's the molar mass of sulfur? I think it's 32.06 or 07.
32.06.
06. And then for four oxygen, that's 4 times 16.00. So let's see what that gives. 63.55 plus 32.06 plus 4 times 16. So according to my calculation, this works out to be equal to 159.61. So this would be the molar mass, all right? Now, the question says that the student measured 40 grams, 40 grams of the copper two sulfate. So we need to find the molar value or the mole value equivalent to 40.0 grams. So 40.0 grams multiplied by 1 mole over 159.61 grams, and that would give the mole. And then we divide that by the 1,000 mils, which we have to convert to liters, which is 1 liter over 1,000 mils. I mean, this will cancel out with that. So let me see what this gives. 40 divided by 159.61 gives 0.25 M. So basically, the student, whoever the student is going down the wrong path. Because the molarity that you're trying to get is 2.0 M. And instead, by weighing 40 grams, the molarity that the student will end up with will be 0.25 M.
So they need to weigh 160 grams.
They need to weigh,
Or no, not 320.
yeah, exactly. Let me check the mirror. I think you're right. 320 divided by 159.
0.25 divided by 2.
Divided by, yeah, same thing, yeah.
8.
Right.
4 times 8 is 32.
Exactly. Okay, so that's basically how that is done. Okay, any questions about this one? Any questions? All right,
Wait, hold on, go back to the other slide. So. Okay, this is the conversion from milliliters to liters.
yeah.
On that.
Okay, so let me give you this assignment here, and I just realized that, well, I'll tell you what corrections you need to make.
Okay, very good.
Okay, here you go,
Yeah, no, we got that.
here you go. Here
We
you
already
go.
has one down at the end. We'll just-
Okay, so I just realized that I included something which we didn't cover, so that would be where it says definitions. Numbers 3 and 4, percent by volume and mass to volume percent, scratch those out, all right? You don't need to worry about those, right?
3 and 4.
3 and 4 for definitions, right? So far, you guys should be able to do question, well, those two from definitions. And let me see here. Okay, so you should be able to do all the questions in the percent by mass concentration section and the molarity section. Okay, so that's what we'll focus on for now. All right? If you have any questions, feel free to ask.
Do you think you could do number 3?
Oh, let me bring it up. Okay, so let me go here. Close this out. Assignments. Save it. Okay, I didn't save it, so let me follow here. Which one you said, number what?
Number 3.
Number 3 on the percent by mass?
Yeah.
Okay, so it says, how many grams of lithium hydroxide are needed to make 25 grams of a 4.0% solution? So let me use Word. Okay, so remember now, percent by mass, or percent will be equal to mass of solute divided by mass of solution. This is one way of expressing it. Times 100%. All right? So basically what the question is asking for is this right here. Right? Now, to get that, what we have to do is multiply the percent by the mass of the solution divided by, divided by the percent, by 100%, I'm sorry. So in this case here, it's going to be 4.0% times the mass of the solution, which is 25 grams, divided by 100%. And whatever that gives is going to be the answer. So that's 4 times 2, 5. Divided by 100. Hold on. And the answer would be 1.0%. I'm sorry, 1.0 grams. 1.0 grams. So basically, to make the solution, you'd have to weigh 1.0 grams of the solute and add water until the total mass is 25 grams.
Is it the same way for like, for how you did the grams for 3, so you do milliliters
I'm
instead?
sorry, what's that?
So for like 4, so sodium fluoride,
Oh, you're talking about
number 4.
sodium fluoride?
Yeah, number
Okay, no, in this case, you'd have to convert the milliliters
liters.
to grams. Now, in order for you to do that, you need the density of water. The density of water is going to be
H2O.
1.00 grams per milliliters, right? In fact, let me erase all this here. Ah. Okay, so what the question is asking for is the mass of the solute. So you're going to use the same formula actually. Percent will be equal to the mass of solute divided by the mass of solution. Now the mass of the solution, well, this one is interesting. Let me see here. Okay, so the question is asking for this, right? And the question says, No, actually, the question is asking for the mass of the solute. And, the percent is, oh, it's multiplied by 100%, by the way. And this will be equal to 3.5%, all right? So what the question is asking for this, so the key thing is the mass of the solution that we need to find. So the mass of solute is equal to 3.5% times the mass of solution divided by 100%. So the key thing is the mass of the solution. Now, okay, erase this here. So to get the mass of the solution, hold on. Okay, this one is interesting because we need the mass of the solution. They gave us the mass of the solvent.
Yes, sir.
Yeah,
I figured a way how to do it.
okay, let's hear it.
So, what you want to do is multiply the mass of the solvent by 100% over 96.5%. So you could get like
Whoa, repeat that.
multiply the mass of the solvent by 100% over 96.5%. So you could
Okay,
get
that's what you're saying. So, multiply by 96.5%.
100% over 96.5%.
Oh, okay. And why would you do that? 100% divided by 96.5%.
Because the final solution is a 3.5% mass solution. So
So the percentage of the solvent would be 96.5%. Okay. So what would this give? Let's see.
I just plugged it into my calculator. It said 25.90673. Just it goes on.
Okay, so the mass of the solvent will be 25 grams because 25 milliliters, you have to convert to grams, which would be 1 mil, 1.00 grams, multiplied by 100%, divided by 96.5%. So this would give 25 times 100 divided by 96.5. So the answer here becomes 25.9 grams. And that would be, hold on. That would be the mass of the solvent, right? So
The mass of the final solution. So the 0.9 over there is just the mass of the solute.
oh, this is the okay, so this would be the
final
mass
solution.
of the solution. Right.
Yes.
And that's because the 96.5 represent that portion which is the mass of the solvent. The 100% would be the mass of the percentage of solution. So this would be the mass of the solution. Now the question is asking for the mass of the solute. And to get that, you'd find the difference between the mass of the solution and the mass of the water, right? So the mass of the solute, which in this case is sodium fluoride, oops, would be equal to 25.9 grams minus 25.0 grams. So the mass of the sodium fluoride would be 0.9 grams. And that's how you do that. So yeah, thank you for pointing that out. All right. Any questions about that one? No? All right.
you think you could do number 3 on the molarity part?
Number 3 in the molarity part. Let's see. Number 3 on the molarity part. 8.885 moles, that one?
Mhm.
Of copper sulfate are dissolved in enough water to make point. Oh, that one is easy. So, in this case here, remember molarity by definition is equal to moles of solute divided by liters of solution. So in this question, they gave you the moles, which is 0.885. And you simply divide that by the volume in liters, which is 0.070 liters, and that's it.
I didn't know if we needed the copper sulfate, like
No,
any of that.
no, because they gave you the moles directly and they gave you the volume.
Okay.
So you didn't need you didn't even need to know the formula for the copper to sulfate. No, if they gave you the grams instead of moles, then you need the formula because you're going to need to calculate the molar mass
Okay.
and then convert to moles.
So like on 5, it'd have to, because it has grams in it.
Right, so you'd have to find the formula for calcium nitrate first. And then you find the molar mass, and then you find the moles. Okay, folks, that's it for today. If you have any issues with the other questions, feel free to contact me. And then we'll continue this chapter. All right, so see you on Wednesday.